Okay, so let me share my screen with you. Okay, I hope you can see my screen. Okay. Okay. Again, Luan, we will go over the questions in a couple of minutes. Be patient, soon. Okay, so officially, my name is Alvis, and I am an application engineer here at CENOS. And welcome to version CENOS 2.0 webinar. In this webinar, we will go over of new features in the new version and tackle a little bit what has been fixed and what is new as well. For new users, we will go over the simple simulation steps with CENOS. We will touch and talk a little bit about what simulation actually is and from what it consists of, and what what does it mean to create a simulation with CENOS. And after that, we will have a Q&A part. Okay, so before we start, I would like to inform you about the PhD modeling school that will take place in the October 14th to 18th in Latvia, Riga, in University of Latvia. And hi, Javad, can you hear me? We were just starting the webinar. Javad, can you hear me? Okay, let's continue. So, Luan, yes, I believe you have heard about this, but just again to go over it. It will be magnetohydrodynamic modeling school, but it will have one course of induction heating, specifically with well, it will be about induction heating modeling using open source tools, which are really useful for future projects with CENOS, because it also uses open source tools as its base. And again, it will take place in the October. It is being organized by University of Latvia from one side and Leibniz University Hanover from the other. And you can register by going to link a.uz/MHD 2019. I will again remind about this course after the Q&A part or during that. So if you have an interest, you can contact me right away or after this webinar in an email, and I will send you the information about this school. Hi, Javad, can you hear me?
Yeah, I'm there.
Okay, good. We were just starting the webinar. I'm glad you made that you made it. Again, we will divide this webinar into 3 parts. The first being an overview of the new CENOS 2.0 version. The second being a short intro of what does it mean to create a simulation in CENOS, and what properties do you need and what can you define to create the simulation in CENOS. And the third will be the Q&A part. So let's start with what's new. So in the new 2.0 version, we have had multiple user interface and user experience improvements. For those who have been using us for a little longer, you might have noticed already. We also have created hints for the first-time users, which will help you to guide through the simulation process for the first time and explain what is what and what needs to be done. Here, as you can see these, you can, of course, hide the hints if you do not want to learn about them. And the main thing that has been changed in the CENOS functionality with the new version is the new geometry creation approach from CAD. This approach allows users to create simulations without actually editing the geometry itself or creating a mesh, because that's being generated automatically. So what does it mean from CAD functionality? It means that you select different geometries, step files that you have created in another CAD creation software. You upload them into CENOS, and in CENOS you automatically create the air domain firstly, and after that you simply need to prepare the geometry for the simulation. And with the geometry preparation, I mean you rename the domains, both volume and surface domains. Firstly, you select and rename volume domains because those will be your parts of the computational domain. So you would be able to define them later in the physical setup. And for each domain, you can go into the boundaries where you can define the surface of each domain, and through that define the boundary conditions for heat exchange, for electromagnetic calculations, for current definitions, and so on. So this is the biggest improvement and the biggest difference from the previous versions. So what has been fixed in the CENOS version 2.0? Actually, since the 2.0 announcement, we have already released 2 new versions. So we are currently at 2.02. And in this time, we have had multiple bug fixes regarding from CAD functionality, which is new. The CSV files, which are part of our results, the templates, and the simulation creation for that, and for the calculation in general, yes. And we have also added the possibility for users to fix the cases if something has been gone wrong in some specific cases. Actually, what I would like to point out, both for new and experienced users, again and again, we have this question mark in the CENOS window, which if you press it and click here to documentation, you can go to our documentation page, which consists of tutorials and how-to articles, which can help you during the simulation setup process, and here you can learn about different functionalities and different parts of CENOS. And as one of the latest additions to these articles is the manual Salome case correction article, which, as I mentioned, is a new approach on how the users can themselves manually correct cases, the simulation cases, in some specific cases. So yes, that's what is new, and that's what has been fixed. We are from time to time updating the documentation page and releasing new articles about things that are not quite understandable and what is new actually. We have also an article about from CAD functionality, which is new for our version 2.0, which you can take a look at. So for the new users, we will go over now also the simulation creation part itself. So let's open a templates case. So basically what a simulation is a mathematical model of a real-life physical system, which describes from one point the geometry of that system and from the other point the physics of that system. And by combining them and calculating them, you can get out the results from this model, which are actually the physical events that can happen and that are happening in that model. So basically the simulation in CENOS is also consisting of these three parts. First, you define the geometry of your, for example, induction system. Then you define that system and each part of it physically by means of material definitions, heating time, frequency, and so on. And in the end, you will get the results, both visual and statistical, about the heating process and the many aspects of it. So let's go a little bit into each part. So the first part is being the geometry part, where you define or create your geometry. If you look at the new case window, you can actually select three sources of how to create the geometry. The first being template, which is open in another window and to which we will switch soon. But basically this is a 2D axial symmetric template simulation, which is fast and which is easy to set up, but can be used only for regular and standard cases for fast heating estimations. The next, from CAD approach, it uses already elsewhere created CAD files, which is also very easy to use, but it has much larger flexibility than the templates. And this is for 3D cases only. And the third advanced geometry editor is for experienced users, because here you directly open our open source preprocessor Salome, which gives you which enables you to fully create and modify your geometry from scratch, as well as create the mesh the way you want. In the first two, the templates and from CAD approaches, the mesh is being generated automatically, so you don't have to worry about that. So let's go back to the template. Not this. So templates are easy in a way that you can simply choose from a predefined template of both workpiece and inductor, and you only need to define the physical properties which have been set for the specific template. You just need to say which one is which and how big, and that is that. You define these properties and you have basically created the geometry, and that's it. If we compare it to the from CAD approach, then here you only need to prepare the geometry in a way that you need to specify which domains are which, and you need to specify the boundary conditions, which both of these things are actually done automatically in the template. So next part is the physics part. The physics part incorporates the global parameters such as frequency and the heating time for the whole geometry. And here you can also specifically define each domain. For example, workpiece and inductor and the concentrators. And you define things such as material or heat exchange on the surface, or for inductor, again, the material and the current flowing through it. As you can see, part of the window is gray, and this is actually the reason why we are encouraging the new users to use templates first, because it is easy to use, first of all, and second of all, some parts are already predefined, so you can focus on the things that are really important at first. But if you are using some of the other two from CAD or Advanced Geometry Editor approaches, then you will have full control over the boundary conditions and everything in the physics setup part. And after you have defined the physical part of the simulation, you click Run, you calculate your problem, and a ParaView, which is our open source post-processing tool, will open. For templates and two-dimensional axial symmetric cases, the results folder, the results window will look like this. The first thing you can see here is the temperature distribution in the workpiece, which has been partially revolved in the window next to it for the better visualization. But that is not everything. You can also look at the different aspects of your simulation. For example, you can look at the current density in the workpiece as well as the inductors. Also, the magnetic flux density can be viewed and things like that. You can, but this is only one part of the results. This is the visual results, which can give you a visual representation of what the simulation results look like. But if we click on the visualization here on the Node button, we can access also the statistical part, statistics of the simulation, meaning the magnetic energy, the active power, the induced current, and voltages in each domain, such as air, concentrators, workpiece, and inductors. And here you can find the information to estimate the power requirements for your simulation, or to calculate things like inductor inductivity, for example. So this was a short overview of what has been created new in the version 2.0, what has been fixed, and what does it actually mean to create a simulation in CENOS. And now we can actually switch to the Q&A part. So let's start with Javad, because I believe you are a new user. So do you have any questions at all?
Do you hear me?
Yes, I can hear you.
Okay. Yeah, so the first question is like about the heating time. What is that
The heating time
exactly? I mean, yeah, I mean like
here.
when the coil is like moving, like the full length of the part, so you call that like the heating time, the total time?
The heating time is the time which is being calculated. The heating time, for example, this is a static heating case. And if you have your system all set up and you turn on the power and the heating starts and you switch it off 20 seconds later. So these 20 seconds are the heating time. It doesn't matter actually if the system is static or moving for scanning as well. The heating time is the full time in which the electromagnetic force works from the inductor on the workpiece to heat it.
Okay. And so if I want to like move the part, like let's say that the heating time is 20 seconds, I want to move the part like 10 seconds faster than the other 10 seconds.
Yes, that can be done. If you give me a second, I will actually open one 2D scanning case just to illustrate what does it look. This. Okay, so from the results point of view, this is one of scanning cases. If we click play, we can see that it is the inductor is moving like this, and from the setup point of view, you can define, yes, for example, if you want to heat the 20 seconds scanning case for the first 10 seconds, for example, with the velocity, let's say 10 millimeters per second, then you define the end time as 10 seconds. You define the velocity and you click run and you will calculate the first part, and then you simply click here to continue from the last time step, which will basically take the temperature field from what you have just calculated. Then you increase the end time to the full 20 seconds, and then you change the velocity, for example, 2 times bigger than the first 10 seconds. And if you then click run again, the CENOS will continue to calculate the case, but with a different setup. And in this way, you can both not only change the velocity, but if we go to our documentation page, we have a specific article about scanning applications, which means that you can not only change the velocity, but you can also heat one part statically and then start the movement, or you can move it in one way and then in the other. So the applications are very wide in this case.
Okay. So I have one more question, is that let's say I have a part and there is a significant thickness variation in that part. Like say that it's like a stepped shaft, but like the difference is really significant. So is it possible to, in your software, is it possible to have at the same time 2 different coils with different frequencies and currents? So uh, one of them is like assigned to the thinner part and the other one assigned for the thicker part.
You can have different profiles and different coils. Yes, with actually different current settings for each part, but I'm afraid that the frequency settings would be one for the whole simulation, meaning that you cannot define different frequencies at the same time yet.
Okay.
But this is actually an interesting application. I will write that down, and if that is what you need for your applications, we can consider it and make it work.
Yeah, you know, because
next
like for
releases.
the geometrically complex parts, maybe we need to like use several power sources
Yes.
at the same time, so they provide different frequency and different currents and even different time. And maybe some of the coils are circles, some of them are squares, some of them are plates, and each of them has their own profile of frequency and velocity.
Yes.
So yeah, that was the purpose of it.
I understand. Yeah. We can simulate that partially for now.
Yeah, okay.
Okay.
Yeah, that's my questions for now. Thank you.
Those actually this induction heating applications with different coils with different frequency and power settings, they would also be your main applications you would want to simulate in CENOS, or are you interested in anything else?
I didn't exactly get your question.
What will, if you would start using CENOS, what would be the cases you would simulate? Would they be similar to what you have just described to me, or do you have any other applications you would want to test?
No. For now, I have like simpler parts, so I'm okay with the features you have right now. But maybe like in a year, when I'm like more expert with the CENOS, maybe I'm going to do simulation on more complex parts, then like more advanced simulation specifications, like the multi power sources and those things will be helpful. But for now, I'm okay. Yeah.
Okay, that's good to hear. Okay, so let's switch to you, Luan. So you have written some questions. Does the question about optimal mesh is the only one, or do you have some other questions? If you create the geometry directly in scenes, as you said, basically, if you're using templates or from CAD, it will help. Basically, it will help to ease the simulation setup process. You will not need to manually create the mesh and define it, and that is the biggest bonus of these approaches. Also, from CAD approach, you do not need to think about the mesh quality or the size of the air domain, for example, which you can automatically create. These things are being taken care of, so it is simpler for you to create the simulation with this. So basically, it in a way shortens the simulation time, but not from the calculation time, but from the definition time, from the definition side. But if you want to refine the mesh even more, then you can, of course, for example, if you're using from CAD approach, then you can click here, the show mesh options, and go into Salome yourself and refine the mesh if you need that, which will also be easier than to create a new mesh, because there will already be a generated mesh for you, which you only need to adjust, not to create it from scratch. So it is faster, yes, but not from the calculation side, but from the setup side of the simulation. And you had another question that how can you perform an optimal mesh refinement so that it works well in a shorter time frame? What exactly did you mean by this? Basically, the calculation time directly depends from the element count. So basically, whatever mesh refinement are you are you creating in your mesh, the main goal would be to decrease the element count of the simulation, because that is basically the only characteristic that will impact the calculation time. There is, of course, the simulation, the physical simulation part. For example, for 3D cases, if you are defining your let's say, workpiece with a full BH curve, not with a constant μ, then the calculation will take a longer time. But actually, in the basis of it, the element count is the only thing that matters, actually, if we are talking about the simulation time. Is that what you meant by this question, or not exactly? So basically, about the optimal mesh, you need to play between two things. The first thing is being the element count, and the second thing is that you cannot make the mesh so coarse that it would not be appropriate for the specific problem you have. Because if the mesh will be, let's say, too optimal, too coarse, it will run very quickly, but the results can be incorrect. So you still need to save some level of resolution for the geometry you are working with. That is also an aspect on optimal mesh, which actually makes some kind of limit to which you can refine your geometry. Have you got? Do you have any other question? Or not for now?
I have another question if he's done.
Maybe he's thinking, but
Okay.
okay, he
We
will
can
just
wait.
write. But yes. What is your question?
So, one thing that would be very cool is that, like, when you start the modeling, like
Mm-hmm.
at like time increment number one, whatever it is, it calculates the temperature, and let's say that the temperature is 500. But, I set the temperature goal like to be 800. So it plays with the current or frequency to reach to that temperature, and like at the end it gives me the profile of frequency or current that with that profile I can reach to 800 all like inside my complex part. You
Mm-hmm.
get it? So
Yes.
yeah.
Yeah, I understand the idea. We have actually talked about this, but not from the perspective of current or frequency, but of the heating time, in a way that you could define, you could not set the end heating time, but you would say that I want the maximum temperature to be, let's say, 800 degrees, and CENOS simply stops when the temperature has reached 800 degrees. We have not talked about the frequency or current profiles,
Okay.
but I will note that, and we will talk about that. So maybe we will implement this in some future iterations. Thank you.
Yeah, so can I find an article about that somewhere in your website?
About what exactly you meant?
About the time you just mentioned, so that it is
That is
just relevant.
not incorporated yet.
Okay, okay.
I
So
mean,
in future.
that was just one aspect of what we were talking, which is similar
Hmm.
to what you said. But if you want to create some sort of research to get for example, the right frequency or approximate the frequencies that you want to use, you can set up different simulations. Let's say you create one case and you save it each with a different frequency. Then you can set it. You can set CENOS to run these cases one after another without the need for you to intervene. And let's say you
Yeah,
can
I think the parametric modeling.
kind of, but not exactly. Parametric, that would be well, CENOS. You cannot say in CENOS rerun this case with different frequencies, but you can create different cases and say to CENOS that I need these run until tomorrow, and CENOS will run each of them successively, and you will have, let's say, in the morning different results which you can compare.
Okay, I get it.
Yeah.
So like I define a batch and then start running the modeling. Okay.
Specifically, yes.
Mm. Okay. And how often do you have these webinars?
We are actually hosting the webinars twice a week, but you need to sign up for them, because if no one signs up, then we are not hosting them. But if you want a specific, let's say, a talk with our engineers or with me, for example, then we can set up a video meeting time anytime. That's not a problem, and we can talk,
Okay.
and we can talk about what
Yeah,
you're
that's
interested in.
great. That's very helpful. Thank you. Yeah,
Yes.
I'm done then. Thanks.
Okay.
So I go mute.
Okay. Luan. Yes. Okay. Oh, you mean that if you have a case and you click close, then it closes. You are right. This actually we have in a way that if you have saved your case, and if you have saved your case, you can close it, and the CENOS will not ask anything. But if you, for example, change some parameter and you try to close, then CENOS will say to you that the case is not saved, and it will ask if you actually want to close, which is, I think, what you have proposed here. Yeah. So you cannot actually close it by mistake. If you can, if you have saved, but in that way you cannot lose anything. You mean when you are running? Okay, that is an interesting idea. Thank you. I will note that. In the meantime, you mean the CENOS has itself closed, or did you accidentally close it? then that I think might be a problem in CENOS part, which is not connected to the closing of a case as much as the problems during computation, which call the CENOS to close. We have seen this, yes, but we are not sure yet why does it happen. If you have a case which with which this happens, then as soon as it happens, please save the case and send it to us, both the case and the log files of that day, and we will see why did it happen, and we will fix that. Okay, do you have any other questions or proposals? There is not yet a way to configure, to personalize your desktop of CENOS, but that is actually an interesting idea, and I will note that. Again, thank you. And I will take this. Oh, you meant about ParaView. There is a way to do that, and I think you did this under File. Not here. Might be the settings. Color RI. This is one place you can do that, but I believe that you need to go not through CENOS, but separately. You open a separate window in ParaView, and through ParaView itself, not through CENOS. And then if you change these things and save them, they should stick. They should stick for all cases. This is actually a state file generated by CENOS, but what it does, it only creates the two windows and the resolution, not the resolution, sorry, but the revolution of the 2D case, and exports the workpiece and inductor domains, but it does not alter the background color, for example, which you mentioned. So I think you can configure that. Yes. Yes, through settings. That was the place. So try that. If you cannot do that, then one way you can look in the ParaView documentation, or you can write me and I will check that out. Okay. Anything else? Okay, if you have any other question, that we have still 7 minutes left. But if no, then I think we can end this webinar. So again, Luan, do you have any other question or not for now? Okay. Okay. So both Luan and Javad, if you have any question at all about any part of CENOS and the simulation setup, feel free to write me to ae@cenos.platform.com or to our support email. That's okay. So thanks for attending this webinar. I hope it was helpful for you, and see you some other time. Thank you.
Thank you. Bye.
Bye.